This is Chapter 3, Problem 51. This is a relative velocity problem, and a little bit with vectors and when you use which component. So in this question, there's a swimmer, and they're swimming across a river, and the river is moving. So the river is moving relative to the shore, the swimmer is going to move, and they tell us the swimmer can, in still water, go at 1.4 meters per second. So that's how fast the swimmer can do their thing through the water. But then the river is also moving, so you got two things going on here. Now I'm going to draw a picture that's a little bit different than the key. If you look at the key, this is a different setup. I'm going to view this as top down. So here's my river, and I'm going to imagine they tell us how fast the river's going. Let's see here. What's the river doing? The current is 0.91 meters per second and carries them downstream. So I'm going to say that the swimmer starts out here at point X. So there's where my guy's going to start. And he's going to try to swim directly across the river. It says that in the problem, that he's can swim at 1.4, and he's going to try to get to the other side, and the stream will carry him downstream. So he's going to try to go that way at 1.4, and the river is going to, in addition to that 1.4, take him down at 0.91. So I'm going to put here on the river, the river's doing 0.91 for now on my picture. We'll talk a little bit more about that in a minute. And the guy's going to try to swim over to he's like, I want to get over here, and I'm going to go 1.4 meters per second. But both of these are happening together, because this is what the guy can do in still water. He's not in still water. So he's going to be going to the right at 1.4 on my picture, and the river's going to take him down at 0.91. So overall, what is he going to do? And I'll define which way is positive here. Up and right is positive. We'll need that in a little bit. He's going to go to the right at 1.4. The river's going to take him down at 0.91. How do we add these two? We go from tail to tip. So that's the velocity of the swimmer and the corresponding direction that he will actually take. So his path is going to be something like this, and he'll hit the shore over here. So he's got an x part to his velocity and a y. He also has an x part to his displacement and a y, and they're similar triangles. They're not the same numbers, but they're going to be the same setup for the triangle. So if this is what he's doing in terms of velocity, you can look at the path I've drawn. If that's what he's going to do the whole time, because these numbers are staying the same, what's his displacement going to look like? Well, he's going to have some displacement in the x, call it x minus x naught. He's going to have some displacement in the y for some overall displacement down and to the right. And that theta will be the same. So if you've got similar triangles here, this is lengths of velocities. These would be displacements. Now, what the heck did they ask us about? That's just all what's going to happen. For part A, it says, how long does it take the swimmer to cross the river? So part A, we want to know how long. Well, when he's going across the river, that how long it's going to take to go across, we're going to look at the simplest possibility, and that's look at just straight across. So what's happening in the x direction? So this is the separation of this x velocity from this y velocity. Well, in the x direction, and in this case in the y direction, he doesn't have any acceleration. But if you're going on my picture across the river here, you know, how long is it going to take to go from here to here? We're looking at the x. Because if you look in the up and down, you never make it across the river. You would just stay in the river if you were just going this way. So we're going to look at the x direction to figure out how long it takes. Since there's no acceleration, similar to a lot of our other problems, just how fast times how long, excuse me, how fast, yeah, that's right, how fast times how long gives you how far. Well, we know Vx, his x component is 1.4 meters per second, and I think they gave us the width of the river. They did, 2.8 kilometer river. So quick conversion over here, 2.8 kilometers. There's 1,000 meters in 1 kilometer. Kilometers cancel, so 2,800 meters. 2,800 meters. And we can now solve for time. So 2,800 divided by 1.4. And there is the 2,000 seconds. Oh, we could have done that one in our head. So 2,000 seconds. And let's check. They may have converted it to hours. 2 times 10 to the third seconds. No, same thing. So 2,000 seconds, that's how long it takes across the river. So it doesn't matter if he's going to swim like that, the way he's doing that with 1.4, as long as that number stays the same, it doesn't matter what this river is doing. The x is separate from the y. As long as he can maintain 1.4 in the moving water, like it's not, not real world where the swimmer might not do as well because there's, water going by him kind of thing. We just have to take that he can still do that. So 2,000 seconds for part A. For part B, I think there was a part B. Let's see, 51. For part B, how far downstream will the swimmer be? Now this 0.91 matters. If the river was going faster, he would travel further down the river before he made it across. Makes sense. If the river wasn't moving at all, it wouldn't be much of a river, he would just be going straight across, and the answer would be 0. So now this 0.91 matters, and this time matters. The one thing that is shared between the x and the y direction is time, because time is a scalar. So it's okay to use this time again, because there's only one period of time to go from here to here. It's the same in the x as it is in the y. So let's look at the y direction, and since the acceleration in the y direction is 0, it's the same equation except for the y direction. So vyt. And again, this is because acceleration equals 0. This is always the equation you're going to use if your acceleration is 0 with the motion equations. So our displacement in the y is what we're looking for. Our velocity in the y is the velocity of the river, so 0.91 meters per second. And our time from the prior part is 2,000 seconds. So our displacement will be our yeah, let's just grab the calculator since I grabbed a number wrong earlier. Times our 0.91, 18 something. So 1,820, and that is in meters. They probably have 1.8 times 10 to the third. Let's take a look. Yep, 1.8 times 10 to the third. So there you go. If you're confused with the stuff above the line, please come in very, very soon for some help on relative velocity. If it's the stuff down here, we've been using these ideas on projectile problems a lot, so help on any problem, not just this one. We'll help you with the ideas for A and B. It doesn't have to be this one, but above the line with the picture stuff and the components, come in for some help on relative velocity. There's not a whole lot more practice with that in the course. These ideas, when the acceleration is 0, to use these equations will pop up again and again and again. That's it.